Have you ever wondered where the building blocks of life on Earth came from? Well, recent evidence suggests that they didn't just magically appear on our planet, they might have arrived from space, delivered by meteorites. Picture this: billions of years ago, our young solar system was full of tiny rocky bodies called planetesimals. These were the essential pieces that eventually formed the rocky planets, like Earth. But it wasn't just rock and metal that these planetesimals brought with them. They also carried essential elements that could turn into vapor at low temperatures, known as volatiles. Volatiles are crucial for life as they include substances like water. So, where did Earth get its volatiles from? A team of researchers led by Raisa Martins at the University of Cambridge set out to investigate this very question. By studying zinc in meteorites, they were able to trace where Earth's volatiles may have come from. Their findings suggest that a significant portion of these crucial elements arrived here thanks to the impact of ancient meteorites. This discovery could be key to understanding not only how life began on Earth but also how it might emerge on other planets across the universe. To understand where Earth's essential elements came from, let's dive into the fascinating work of Raisa Martins and her team. They decided to focus on zinc, a chemical element that can reveal a lot about the origins of Earth's volatiles. But why zinc? When zinc forms in meteorites, it carries a unique signature that tells scientists where it came from in the solar system. By tracking zinc's presence in various meteorites, the team hoped to piece together the story of how Earth gathered the ingredients needed for life. What they found was remarkable. Zinc on Earth doesn't have a single origin, rather, it appears to have been delivered by planetesimals from both nearby and distant parts of our solar system. Around half of Earth's zinc likely came from planetesimals that formed closer to the Sun, right alongside our planet and the other rocky worlds. However, the other half is a bit of a cosmic wanderer. It likely originated beyond Jupiter, in the cold outer reaches of our solar system. This mixture of zinc origins gives us a clue about the varied sources of Earth's volatiles. Early planetesimals that formed near the Sun were exposed to intense heat and radiation, causing them to lose most of their volatiles through vaporization. But those from the outer solar system were better at holding onto these precious materials, as they didn't melt as much under the Sun's powerful radiation. So, as these later arriving planetesimals collided with Earth during its formative years, they delivered not just rock and metal but also a healthy dose of volatiles, which included water and other life-supporting compounds. In short, the combination of planetesimals from different parts of the solar system might have given Earth just the right mix of ingredients for life to eventually flourish. This finding could help scientists not only understand how life began here but also guide their search for life on planets around other stars. After all, if these processes played out in our solar system, they might be happening in others as well. As we explore how Earth accumulated the essential ingredients for life, let's take a closer look at the role of planetesimals in shaping our planet. When Earth was forming, it went through a chaotic period of constant bombardment by these ancient space rocks, each carrying a mix of elements that would ultimately create the conditions needed for life. Through meticulous research, Martins and her team discovered that around 70% of Earth's mass came from melted planetesimals, which were stripped of most of their volatiles due to intense heat. Surprisingly, however, these planetesimals only contributed about 10% of Earth's zinc. So, where did the rest come from? The remaining 90% of Earth's zinc, and likely a significant portion of other volatiles, was delivered by unmelted planetesimals. Unlike their melted counterparts, these planetesimals retained a rich supply of volatiles. This is a crucial discovery because it implies that Earth's early atmosphere and oceans were likely formed from materials originating in the cooler, more distant reaches of the solar system. This journey of zinc and other elements to Earth wasn't a random process. It took place over tens of millions of years as our planet was still gathering material. During this time, Earth's surface was bombarded by different types of planetesimals. Those from farther out in the solar system brought with them the critical volatiles that would become the foundation of our atmosphere, oceans, and ultimately, life itself. The interplay between melted and unmelted planetesimals highlights how Earth's chemical makeup was shaped by diverse sources. It's almost as if the planet was selectively gathering the best elements from various regions of space, creating a unique blend that would make life possible. This also raises a fascinating question: could other planets in the solar system, or even beyond, have undergone similar processes? If so, they might also have acquired the right volatiles needed to support life. By studying Earth's formation, we may be uncovering clues that could help us find life in the vast expanse of the cosmos. Let's take a step back and consider what this all means for the search for life beyond our own planet. The discovery that Earth's essential volatiles likely arrived from a mix of inner and outer solar system materials offers new insights into where life might arise elsewhere. It's not just about finding a planet in the habitable zone around a star anymore. While the distance from a star is still critical, it determines whether liquid water could exist on a planet's surface. Our findings reveal that there's more to the story. The presence of essential elements like water and other volatiles depends on whether a planet has the right blend of materials. In our solar system, Earth was fortunate. It collected enough volatiles from unmelted planetesimals to form oceans, an atmosphere, and eventually life. However, as Martins points out, having a planet in the habitable zone doesn't guarantee that it has all the necessary ingredients for life. For instance, a planet could be the right distance from its star but lack the materials needed to support life due to a different formation history. If a planet didn't receive enough volatiles, or if its primary planetesimals came from a region that lost most of these elements, it might be barren, regardless of its position relative to its star. This has significant implications for our search for habitable worlds. When scientists identify planets orbiting stars in their habitable zones, they usually focus on surface conditions like temperature. But the findings from Martin's team suggest we should also be looking at the types of materials these planets are made from. Did they form from planetesimals that had high volatile content? Were these materials a mix from both the inner and outer regions of their solar system, as Earth's were? Answering these questions could bring us closer to understanding the potential for life on those worlds. Moreover, the processes that brought volatiles to Earth could be common across young planetary systems. As stars form and their surrounding disks of dust and gas evolve, planetesimals begin to coalesce. Some will inevitably melt under the heat of the nascent star, while others will remain cold, preserving their volatile content. If these same dynamics occur elsewhere, we might expect other rocky planets to have received similar deliveries of life-supporting volatiles. However, the exact mix will depend on the unique circumstances of each system, its distance from the central star, the types of planetesimals present, and even the timing of those collisions. In essence, our solar system could serve as a model for understanding which planets beyond it might also be capable of hosting life. Yet, while Earth's story provides clues, it's also a reminder that the formation of life is a complex process that may not play out the same way twice. Still, by studying our planet, we're gathering a toolkit of indicators that could point us toward other worlds with similar potential. The exciting part is that we're just beginning to scratch the surface. As we refine our understanding of these cosmic processes, we may find that the conditions for life are more common than we once thought, or perhaps that Earth is even more unique than we imagined. As we wrap up this exploration of Earth's cosmic origins, we're left with a profound realization: our planet's journey to becoming a cradle of life was far from ordinary. The story of Earth is a mosaic of ancient elements and cosmic events, brought together from every corner of the solar system. But it's not just Earth's past that captivates us, it's the potential futures of countless other worlds. The findings from Martins and her team offer a new lens through which we can view the cosmos. Now, when we look at distant stars with orbiting planets, we can wonder not just if they are in the right location but if they carry the right mix of elements to spark life. Did these planets experience similar cosmic deliveries of volatiles, carried by ancient planetesimals across vast reaches of space? Are they harboring the conditions necessary for life to arise, waiting for the right moment, the right combination, to come to fruition? These questions fuel the search for habitable worlds beyond our own. By understanding Earth's history, we're developing a blueprint for identifying other planets that might host life. But let's not forget, this journey also deepens our appreciation for the delicate balance that made life on Earth possible. It's a reminder of how special our home truly is and how, amidst the vastness of space, the right circumstances came together to create a planet teeming with life. So, where does that leave us? With our gaze set firmly on the stars. Each new discovery inches us closer to answering one of humanity's oldest questions: are we alone? As we continue to explore and learn, remember that these cosmic puzzles aren't just scientific curiosities, they're part of a much larger story, one that connects us all to the universe. If you're as fascinated as I am by the possibility of life beyond Earth, why not join the conversation? Follow our journey as we delve into the mysteries of the cosmos, explore new frontiers, and uncover the secrets of our existence. Subscribe, like, and share your thoughts on what you think might be out there. Together, let's keep looking to the stars, because the answers we seek might just be waiting in the space between them.